AB Calc 2.6, day number 2 notes. We're going to work with continuity and dealing with an unknown. Let's look at example number 1. Let f be the function defined below, not above, where c is a constant. For what value of c, if any, is f continuous at x equals 2? Okay, so let's make a quick assumption. Let's assume that f of 2 exists. For continuity to occur, f of 2 must exist. Okay, now with regards to continuity, what we want is for this piecewise function, the limit coming from the left of 2 of f of x to equal the limit coming from the right of 2 of f of x. So the function coming from the left for f of x is the limit as x approaches 2 from the left of x squared sine of pi x, and limit coming from the right as x approaches 2 from the right of f of x is going to be x squared plus cx minus 18. So what we're looking to do is make sure that these limits are equivalent. Okay, so what we have to do is evaluate with a direct substitution. So if I substitute in a 2 on the left side, I get 2 squared times sine of 2 pi. And on the right side, I get 2 squared plus 2c minus 18. Now sine of 2 pi is 0. Therefore, I'm getting 4 times 0, which is 0. And on the right side, I get 2c minus 14. Now, when I solve for c, this will be the value for c such that f of x is continuous at x equals 2. So I'd solve, so 2c is equal to 14, and therefore c must equal 7 in order for f of x to be continuous at x equals 2. Okay, let's continue with example 2. The function g of x given below is discontinuous at a value of x. Redefine the function so that it is continuous for those values or value of x. Okay, so where potentially could this function be discontinuous? I would say a good guess would be at x equals -3. Okay, so g of -3 clearly does not exist. So we need to redefine g of -3 so that it does exist. So right now that's an issue with continuity. So what we need to do is we need to look at the limit as x approaches -3 and plug that value with g of 3. So the limit as x approaches -3 of g of x doesn't exist, but what I want to do is I'm going to factor. Okay, well, first of all, I guess we should show why it doesn't exist. Okay, if I plug in a -3, okay, g of -3, well, what does it equal? It equals 9 minus -3 minus 12. Okay, so, and in the denominator we get -3 plus 3. So we're getting 0 over 0. That's telling me that there's going to be a hole in the graph here. Okay, so since the limit does not exist, at least according to our initial indeterminate value, what I'm going to do is I'm going to factor the numerator, which would be x minus 4 and an x plus a 3. And I'm going to reduce out that hole, and therefore I can reevaluate and I will get a limit of, let's see, -3 minus 4, that'll be a -7. So in order for part 3 of the continuity checklist to check, so to speak, I've got to plug the gap here, because right now g of negative 3 doesn't exist. So if I want this to be true, and this is equal to 7, then g of negative 3 must be equal to 7. Therefore, g of x will equal, that wasn't my best set of braces, let's try that again, that's better. Okay, g of x will equal x squared minus x minus 12 over x plus 3 when x is not equal to negative 3, and when an x is equal to 3, we're going to then have an output of negative 7. Okay, let's look at another example on the following, I guess it's on this page. The function g of x is given. It is discontinuous at one value of x. Let's redefine the function so it is continuous for all values of x. Okay, so as I initially just look at this, I think of an issue within the function itself where if I have x equals 0, I'm going to have a discontinuity. Okay, so right now, g of 0 does not exist. Okay, so I'm going to find a new value for that. And I'm going to find that by finding the limit in part 2 of the continuity checklist as x approaches 0. If I can find out what that value would equal, I can then reassign g of 0 to be that value, and now we've got continuity at x equals 0. So let's take the limit as x approaches 0 of e to the 1 minus cosine of x over x. Okay, and using some properties of limits, I can work with this and make it a little bit easier to work with and manipulate. I'm going to take e to the limit as x approaches 0 of this expression, 1 minus cosine x over x. Okay, and then from there, I'm actually going to do one more manipulation. And I'm going to take the limit as x approaches 0 of 1 minus the limit as x approaches 0 of 1 minus cosine of x over x. Okay, at this point, hopefully, maybe we haven't gone over this, I'm not sure, but this is a special limit. This is a special limit that you should put to memory. Limit as x goes to 0 of 1 minus cosine of x over x is actually equal to 0. Therefore, this is e to the limit as x approaches 0 of 1, which will be 1 minus 0. So our limit equals e. Therefore, the limit as x approaches 0 of g of x is equal to e. Thus, for g to be continuous, at x equals 0, we want the limit as x approaches 0 of g of x to equal g of 0. So what we're going to do is redefine g of 0 to equal e. Therefore, g of 0 must equal e for discontinuity. So here's the definition now, redefining g of x. Okay, so g of x will equal e to the 1 minus cosine of x over x. That'll happen when x is not equal to 0. And when x is equal to 0, we're just going to reassign the value e to that. Okay, let's continue on the next slide. All right, final example for today. Example 4, let f be the function defined below. For what value of a is f continuous at x equals 2? So if f of x is continuous at x equals 2, then the limit as x approaches 2 of f of x must be equal to f of 2. So since in the context of this problem it's telling us that the function is continuous, therefore we can assume the limit exists. We can assume that the output f of 2 exists, and therefore we can assume that we're finding a value that makes this equation true. Therefore, the limit as x approaches 2 of x squared plus 3x minus 10 over x minus 2 must be equal to f of 2, which is 4a. So I want those two to be equivalent. I'm going to factor and reduce, because I believe if I plug in a 2, we're going to get 0 over 0. So I'm going to factor, which gives me x plus 5 and an x minus 2. Again, should be equivalent to 4a. I reduce out the hole in the graph, and therefore the limit as x approaches 2 of x plus 5 should be equal to 4a. I'm going to evaluate this limit, which would be 2 plus 5 equal to 4a. Therefore, 7 equals 4a. Therefore, for f of x to be continuous at x equals 2, a must equal 7/4. All right, there you go, guys. That's working with continuity and an unknown. I would do some practice in the homework, practice problems involving intermediate value theorem. If you got any questions or concerns, please contact your teacher. We'll see you in the next video.